Hey everyone, today we're going to be doing a demo of our VPSS 3i solution. This will cover the bending and the blanking side and a couple different aspects of the application itself. To start, we're going to be working in our Material Explorer. So I want to show you this just to kind of give you a background of exactly what this software is doing, how it's processing our 3D models and getting some of the data that it's going to use for post-processing once we get into the CAM side. So in our Material Explorer, we're actually going to load in certain material types that we use in our facility. Each one of these material types actually has a list of different material properties. These all get loaded by default, but you can adjust them if you get that particular information from your steel supplier. We're actually going to use this data later on to calculate our bend deductions. Once we load in our different materials, we're going to assign thickness to those materials. So each one of these materials is actually going to have a thickness value added to it. That way we can register, hey, we've got aluminum, 16 gauge, 14 gauge, and so on. And that material name that gets associated with that type and thickness is really what's going to carry the rest of the data through the system. Once we add in our different material types and names, we'll be able to populate sheets. So we actually have a batch creation setting, so we can set some default sheet sizes with our size master. Anything in green here is a default size. Then we can do batch creation, choose our different material types, select the applicable sizes, and hit OK, and it's going to generate these sheet sizes to be used later on once we get into the blanking side. Finally, once we have our sheets done, we're going to use Amada's bend deduction calculation tool to make sure that we're getting the correct flats as we unfold your 3D models. So what I see a lot of in the industry is engineers are submitting 3D models, and these parts may or may not be designed for manufacturing. See a lot of varying bend radiuses, K-factors, bend deductions, a lot of different values being used. A lot of times they don't know exactly what we're doing to manufacture these parts and what machines we're building them on. So what Amada's done is they've kind of taken the manufacturing side out of the engineer's hands and gave that back to manufacturing with the VPSS 3i solution. So essentially what we're going to do is we're going to load in our different material types. So we can load in a material name. We'll be able to give it what our actual achieved bend radius is, so the engineer doesn't have to try to keep a chart next to him saying, all right, with 12 gauge we have this bend radius, quarter inch, we have this bend radius. We're just going to go ahead and identify that on our side, so they can just draw their model the way they need it, and we'll take care of the rest from there. We can also associate it to a particular V-width that we may be using for that material type or thickness, indicate whether we want bend deduction on one or both sides of the bend, and then we can simply do a calculate, set an angle range that we want to do the bend deduction calculation for. And now this is where it's really neat. We can actually go back and look at our press brake tooling library. So we can go in and look at the punch that we're using with that individual punch radius, and we can select the V-die that we're going to utilize. And it's going to pull in that shoulder radius, V-width, and bend angle. And so it's actually going to be calculating the bend deductions based off the tooling that we are actually going to be bending these parts on. That gives us a very precise idea of what that material stretch is going to be as that material is forming in the press brake. So we'll let this calculate, and we'll get that data point here, and you see how quickly we got a full library of bend deductions for each individual angle. It gives us what the angle is and then what that calculated bend deduction is. Now if we have a couple of bend deductions that we feel that maybe we've changed our process at our own facility and we'd like to fine-tune that a little bit to meet our own needs, for example on this 064 bend radius for my 90-degree angle, I can actually just double click on that one and say, well, to really fine tune, we actually have an 062 bend deduction here. And we can make those changes to individual angles, or we can actually just add in a specific angle and provide that bend deduction at that angle. Once we have that data inputted in, everything's pretty simple from here. We are just going to load models in. It's going to go back and look at all this information in the background, and it's going to calculate our flat patterns accordingly to the data that we've inputted in our Material Explorer. So let's jump over to Production Designer. So over in Production Designer, this is where we're going to be able to import in solid models, assembly files, DXF, DWG, pretty much any sort of standard CAD file that you're going to see in the industry, step file, IGES, ProE. We can look at all the different file formats here. So we've got a number of different supported files. This is just on the 3D side. And for demo purposes here, I'm going to go ahead and load an assembly file. So this is just a regular SolidWorks SLD ASM file. It's got the associated parts here in the folder. I'll load this assembly file in. So with this assembly, essentially right now, we are looking at the actual native SolidWorks file formats here. And what we need to do is we're going to process this through. We're going to do a batch process, so it's going to do this automatically for these 3 different components. But we're actually going to be converting our SolidWorks data, an SLD, PRT, SLD, ASM. We're going to be converting that into SEM data, which SEM, which is a sheet metal engineered model, and that's essentially the 3D file format that Amada uses, not only in our software, but out of our equipment as well. So we're going to be converting this into smart data that's going to have all of our bending and blanking and welding and robotic information all tied to it. We're going to apply some different methods of manufacturing and the order in which we're going to do that. And then we're going to be sending that out into the CAM system so we can actually make programs for these machines. So let's get the process started. In our batch process, it's going to go through and it's going to break out each individual component. This is where we might see some hardware. It's going to throw that out. We're not going to have to worry about separating hardware or other features out in this method. It's just going to show us the sheet metal parts with those individual thicknesses. So for each thickness, it recognizes that thickness. We just have to let it know what type that is. So in our case, we'll just run this as cold rolled, and this part will be cold rolled as well. So now we've got our parts associated with type and thickness, so it knows what these parts are and it knows how to apply the data from our Material Explorer. So I'm going to select OK, and the process is going to start. So there in just, really a few seconds, it broke down each one of these individual part files. It assigned material and thickness to it. You can see the colors changed here in my next set of information. This is showing that it converted this data into SEM data. Down here it applied the method pattern. So what the method pattern is that's basically identifying the methods of manufacturing. So that is, are we going to have any forming tools that we need to do on our combination machine? Does this have a laser assignment, maybe some hole destruct data or different information about that part that we're going to have to process different on our laser? Are there any bends on this part? A Z bend, a hem and flatten bend. It's going to pick up on all those different methods of manufacturing and basically pack all that data into this SEM file, so when we get into that CAM system, it'll automatically be able to program these parts based on all that data built in on the SEM file. Here it's shown that it was able to create an unfold. So if we were to go back and look at these files, which we will in a moment, you'll see it has all that bend deduction data and all that crucial information at that area of forming. It's going to have all that built in this unfold diagram, so that when we send it into blank cam, we know that we're cutting correct flats that are going to bend up correctly on our press brake. Finally, it just gives us some information on where it saved that data. So here I even have it set up where it's going to save out some DXF files. Maybe I'm going to send that out to my FabriVision to get scanned for quality control, or some other application I need to reference these DXF files in. But we can see in my Windows Explorer here, I had these DXF files dropped right into this location for use on my FabriVision or elsewhere. And then here just gives us there it was 21 seconds of process time. So that's a lot of data processed in 21 seconds to go from a solid model to usable data in our CAD/CAM system that we know we're going to be able to make good programs with. So let's jump over to making a program now. Here in my A Planner, we're on the blanking side, so we're going to make some laser programs first. So what I'm going to do is go to my product/parts, and what's neat with our process here is that we can actually load in an assembly file. So an assembly file, that's not necessarily just an assembly of individual components. It could be, as I have in this example, just a collaboration of different parts. So we could look at it as maybe a production schedule. You could load in 4, 5, 10, 15 different models that maybe you're going to run for the day or run for the week, and you could process them all together, and it's going to keep those parts grouped together and respect the needed quantities of those parts as we get into the actual CAM site here in the A Planner. So I'm going to select a couple of assemblies here as a demonstration. We've got this base assembly, so we just ran this through in our production designer. Here's a cabinet assembly, so here you can see we have a couple of repeating parts, so it knows that we have multiple of certain components in this assembly. So I'll select both of these assemblies. We're going to register these and open them up. So now it's going to take that flat data that it got after it calculated those bin deductions, and it's going to drop them into our A Planner. So here it shows, each of these parts per assembly, there's one component, except for this part, there's actually two of this part in that particular assembly. So what's neat is, it knows what those individual required quantities are from this assembly file. I can simply select this particular assembly and give it a lot number and say, hey, we need to make 25 of this assembly and 35 of this assembly. And now it's actually going to be multiplying these quantities out at the correct lot number size, so that we know we're manufacturing the correct number of parts and there's no fat fingering anything or putting in the wrong quantity by accident or reading a work order incorrect. It has all that tied together right from the start from a good solid model sent from engineering. So now we can go ahead and get right into our auto nesting. It automatically knew what all of our material types and thicknesses were and associated that with a cutting condition of the machine. All of that data is directly available in our software because we're directly connected to that machine. We can immediately get all that cutting condition information. So really all it needs us to select is what sheet sizes do we want to allow it to nest on. We can select all of our sheet sizes, and it's going to try to look and see what the best maybe the best utilization is going to be on some different sheet sizes. We can just select standard sheet sizes. We can even go through and choose maybe like a remnant sheet. So here we've got a remnant, or even a skeleton. We could have it try to nest parts onto a skeleton sheet that we have saved in our library. Because as we're creating these programs, it is saving these skeletons back for reuse in the future. Same thing with our remnants. So we'll select a couple of these and see if it nests any parts on them. So now as it's generating its nest, the blank cam is really, the ultimate goal is just a one-click solution. So it's not only going to nest all of our parts, it's going to apply all the laser, turret, combo, whatever machine we're nesting on. It's going to apply all those tool assignments all in one click. It's also going to, on the laser, it's going to look at your slat locations and such. And if there's maybe an opening that is at risk for tip up, it'll slug destroy that opening or put tabs on it depending on what your preferred method of manufacturing is. It's going to generate all of our NC code, nest all these parts out, apply our remnant cuts, a number of different features all happening at once when we do that auto nesting. So here we kind of have a general overview of all of our different nests that it created. Here you see it was able to select that skeleton sheet that we selected, so it nested those parts around openings that were already in the sheet. It applied a remnant cut to a sheet that we had left here that, you know, we'll be able to reuse this sheet later on. See, on this particular part, it applied the slug destroy to this opening where maybe it was at risk for a tip up because it's only on a couple of slats here, just barely hanging on to 2 slats. There's a risk there that it might fall down through and, you know, have a collision with the laser head, so it did slug destroy those openings. And we've got some other parts here that we have some etching applied to. That's already saved with that part, and it automatically applied that etching. If we do want to do some manual editing of a part, we can simply double click on it and we can get into the individual part edit. So here we can do things like move tabs around, add additional tabs. We can add etching. So like this, we'll just do the part name here and place that on the part, and then we get etching on that particular component. We hit finish here, and once we go back into sheet edit, you'll see it's going to prompt us, do you want to apply these changes also on the other parts? So when I select yes here, it's going to look at all different angles, all different sheets, all different instances of that part, and it's going to apply those changes. So another feature we might want, we'll just maximize this sheet here, is to be able to quickly do things like common line cutting. So for example, you know, these parts have a straight common edges here. That would be good for common line cutting. Right here in this sheet edit mode, we can go into common cut, select 2 edges of a part. It's automatically going to link those edges together and generate a common cut program for these parts in this sequence. So we apply this and finish. Now we have a common line cut set up for these individual parts. Very quick and easy. If we look at another sheet, like for example, maybe on this sheet here, if we wanted to change this remnant or do something different with this remnant, go into our remnant cut, clear out what's on there. If I want to add one, we could do a multi-line remnant. You know, to reapply one here. Or maybe we just want to space these parts out so that we're using up more of this sheet. In which doing that, we can do wider spacing. And, you know, this is a little bit of a dramatic example, but you can see that it spaces those parts out evenly across the sheet so that you don't have as so much integrity of the sheet being used. Here we'll just do re-nesting on this particular sheet. And you can see it immediately changed this sheet back to the way that it was when we started. And look at all of our different nests. If we did want to, you know, maybe add components here, we could do an import part. It's going to load up our database. We can go through and look at all of our different parts that we have. Open those up and actually just drag them right onto the sheet. We could even bring this straight down to the edge here, lock that in, do a grid. We'll click on the part, do an auto calculate. See, it'll fill this rest of the sheet up with that part. And now we have a gridded nest of this component. One thing you'll find too with the 3 eyes, as we move parts around, see it automatically snaps into location. We turn our direct assignment on and move it here. See, we get a red rectangle around components when there's a collision. So even from a distance, we have a clear view of any sort of issues that there may be on a sheet. Once we're all finished up with our nest, if there's nothing else that we want to change, we simply hit NC Create, and it's going to save these programs to our machine as a schedule, so we can just immediately go out to our laser, load this into our controller, and it's going to know what material to run, what material size to run, what the NC code is, and the automation is just going to go and grab material out of the tower, load it onto the machine, and it's going to start making parts. Alright, once we're finished with that blanking program, now we're going to want to make press brake programs for each of these parts. So we'll jump over to our bend tab. We can see we still have our parts here. It's got that material information. We can choose our different machines from up here. We simply select all the parts, and then we'll do an auto program. Other option here is, common layout, which is where it'll try to make one single tool layout to bend all of these parts. We can also set up full auto, where it's going to look for new programs or new parts can dropped into that server and automatically generate programs. So after it's finished up with all this auto programming, we're basically going to get one of three results. We're either going to have OK, which means that it made a program, no problem, it's ready to run out of the machine. We're going to get OK warning, which means, hey, we were able to make a program, but there might be something here that you need to review, so it's worth taking a look at before you run it out of the machine. Otherwise, we're going to get no good, which means, hey, there's some reason why we can't figure out how to make this program. You're going to have to review this manually, put your own tooling in, find your own sequence, or maybe even send this part back to engineering to see if we can look at the designs that might not be manufacturable. So let's take a look at one of each of these quick. So here's an example of a part that it was able to get a green light program on. You can see it has all the different bends assigned here. It recognized that these tabs are both on share the same bend line. So it did do those in one hit. We'll simulate it here. We'll see it should use both of these tool sets actually. So we'll run a quick simulation here. You see it is applying our bend angle reader here, so we're make sure we're getting accurate angle readings. Everything looks good here. If there's anything you want to change, you can move things around manually here, move your back gauges around, kind of change some of those positions. You can move your tooling around if you desire. You get a lot of control on what you can do here, but otherwise we'll just close out. It'll prompt you to save, and then we're back into our main screen. Here we'll check out one of the warnings. So here it's alerting us that there's a bend without a back gauge. That may be a problem depending on your operator. So here it did select tooling. It does have a part on here, so in this particular case it looks like this first bend is without gauging. Was able to get the rest of the bend, so if we jump back to that first bend, we rotate this around, we can see we might not have much of a flat area there to actually put the back gauges on. But we'll come in and go to our back gauge and say manually assign, click this edge, and we can still force those back gauges to come up here. Maybe we want to run this part on the side of the die, so we have a little bit more of a side gauge, so I can actually zoom in here and select the part and say alignment. I'm going to bring this side of the part over to this side of the punch, and it's actually going to bring that edge of that part all the way over. That way we have something to line it up against while we're bending it. We can even come here and maybe even move our back gauges around a little bit. This back gauge right on the side there. So that way we're a little bit squared up on how we're going to bend this part. Once we make any changes that we need for a warning part, we can do one more final simulation, close it out, and we'll go ahead and save the changes. And once we save these changes, that's immediately available out of the press brake. So we make this program. The green light ones, they are good to go. They're already out of the press brake. We can walk out to the machine and start running them now. These ones we are reviewing. Once we save that, then we'll be able to go out to the machine and actually run these parts. Finally, we'll look at one of these no good programs. So here it just gives us kind of a clean slate. It's saying, hey, here's your machine, here's your part, but we couldn't find a solution. So what we can do is we can select a bend line, go into our tools, and actually load some tools in. Pretty quick look at our library. We got this auto screening feature when we're selecting tools, so it knows what that material type and thickness is, and it knows what tools you're allowed to use based on bend force. So I usually leave this auto screening on so that I can select tooling that is going to be safe to bend with. Once we come in here, we'll look at a side view here. And we can turn some different machine features on or off so we can get a good view of this part. And if we apply some sequencing, do each individual bend. And let's take a look at this last bend here. You can see if we go into our feasibility check here on current bend, see we get particularly this collision face of punch. So it's showing us that this return flange on this part is actually running into the punch. So that's an example of a situation where the auto program is not going to generate this. Anything that's at risk of damaging the part, damaging the machine, or harming a human being, it's not going to generate an auto program for. But we can manually create this programmer, and maybe as a press brake operator myself, I'll look at this part that's made out of 20 gauge and realize, yeah, you know, it might be slightly running into that punch, but it'll just put a little bit of a back bend on this part and I'll be able to squeeze it together, or whatever the reasoning may be. If it's something that we approve of, we can still write this program and save it, and once we save that, we'll be able to go out to the machine and run it, and this is what the operator is going to see as well. So once we're finished evaluating this part, we'll close out of here. And the rest of these parts are all ready to go out of the machine. So let's get out of A Planner, and we're going to jump back over to Production Designer to just look at a couple more features with importing in files. So back over in Production Designer, I wanted to show you some of the tools that we have when importing in 2D data. A lot of people are still getting DWGs, DXFs, which the DXF files, we can directly load those into A Planner and make a blank cam program. But what about those DWGs? Maybe some of those drawings that you get that don't have a flat pattern. Maybe they're not real clean. They've got dimensions, title blocks, things like that. The kind of the good, the bad, and the ugly of manufacturing here. So let's take a look at one of these files. So here's a orthographical view drawing. And when we open this up, this is something that's pretty hard to work with as a CAD programmer. So yeah, you have an image of what this part's supposed to look like. You've maybe got a couple of dimensions on here of what the overall sizes are, maybe some radiuses. You know, you've got a few pieces of information. but not really enough to actually draw this up. And even if you started drawing this, it's going to take a while to get this redrawn in 3D CAD and then export it out as a DXF or whatever, so that you can try to make programs with it from there. So let's see what we can do with it in Production Designer. First thing I want to do is I want to clean this orthographic drawing. So I want to try to get all the junk off and just get the main views that I need. So by selecting this button, you see it grabs each individual view that it feels is relevant to how we're actually going to make this part. So now we'll extract that orthographical view drawing. It's going to drop this isometric view off, so we're just looking at our three sides. And now we're going to do an auto solid. Now this is really neat. It's going to immediately pick up this material thickness. We can change the type if we want, but it automatically detected that thickness from that view. And it actually is building this part off of that view. So it's got all those different flanges, the material thickness, the different sides. It's building this from that orthographical view drawing. So now we have our part with all of our surfaces. Every now and then, I mean, you're bringing in just basic 2D data, so every now and then we might just need to give it a little bit of help. It looks like on this particular part, it grabbed some faces here. It knew those were there, but it wasn't sure on what this was for a bend radius maybe, or if this was a bend here. So all we got to do is give it a smart corner, say, hey, this is actually a bend here. Do an add bend, and you can see it's going to add that in for us. Come over to the other side, do the same thing. Add our bend in there. And down here on this last flange as well. So there, in just a matter of seconds, we had a pretty terrible orthographical view drawing with no flat pattern. And now we've got a fully usable 3D model. What's great even is I can actually export this 3D data out, and I can save this to open this up into another 3D CAD system if I want to do some other modeling with it. Here I'm going to move to the method, and this is where it's going to apply that method of manufacturing. So if we look in these details here, it's going to look at blanking, clinch fastening, welding, bending. There's a number of different methods of manufacturing it's going to try to identify in this process. If we had any hardware or other features in here, this is where it's going to recognize those features as well. So you can see when I go and select on a particular bend, it knows what that bend deduction is from our Material Explorer. It knows what V-width we're going to use. It has all that information all built into this file immediately from all the data that we entered in from our other parameter settings. So now we can generate an unfold diagram. So again, in a matter of a few seconds, we went from an orthographical view drawing to a usable flat pattern that we can send directly into BlankCam. So here in BlankCam, we can just do a quick parts grid, auto calculate, finish. We got this sheet filled up with parts, NC create, literally done. We can send this out to the machine right now and go run the nest of this part. Once we're finished, we'll move back to the method, jump in the part, move over to BendCam, choose the machine that we're going to run this part on. Now we'll do an auto program. And again, in a matter of a few seconds, we've got a program ready to run out of the press brake. All we got to do is save this, and we can go out to the machine and start bending this. And literally, the customer could have brought that file in on a flash drive, and you go out and give them a tour of the shop, and by the time you get back around to the front door, you could have this part sitting up at the front desk ready to go. From pretty much any CAD source that you encounter, Production Designer has a way to handle it. Alright, so finally, we're going to open up another 3D model here and just quickly show you what it's like to add some hardware into a part. Here we're opening up our 3D model. Select the primary face or detect that material type and thickness. Here on the left we have our original solid model, or I'm sorry, on the right we have our original solid model. On the left is our SCM model. This is just kind of a comparison screen to make sure everything looks like it's supposed to. We'll confirm out of there. And then what I'm going to do is actually add some hardware in to where these holes are. Maybe that's where some studs are going to be, and maybe we're going to put those in before we bend the part. And we want to make sure that when we run this on the press brake that those studs aren't going to interfere with any tooling. So I'm going to go into my hole chart, detect the holes. I can select this particular round hole. It's actually a threaded stud. You can choose one from you can build favorites, or you can add new ones. Select OK, you can choose your direction and such. Close out of here. Now you can see that we actually have a couple studs on this part. So we'll move over to the method. And once we get to the method, it's going to look at how it recognizes that particular stud and when we're going to insert it. We can say, hey, we're going to do blanking, clinch fastening, and then bending. Or we could even say we're going to do clinch fastening after bending, and then we're not going to see it in the processing and bend cam. Or if you don't want to see it, you can always delete it out as well. But from here, we'll go into the bend cam, select our machine again, and now we can generate this program, and we're actually going to see this hardware in the program that we create. And furthermore, when the operator is running this program out of the machine, when they pull this file up that was generated in 3i Bend, they'll be able to see that hardware while they're operating as well, which is not only good for detecting interferences or maybe separating the tooling out so a stud can fit between, but also helps with making sure they're bending the part the right way, because they can see right on the screen which way that hardware is supposed to be facing as they're bending the part, and it gives that operator a little reassurance as they're manufacturing the part. So again, once this part completes, we can run a simulation. You can see that hardware in there, the bend angle finder running. Then we simply save this part, and it's ready to run out of the machine. So that covers our demonstration of a VPSS 3i software package for the bending and the blanking side. If you have any other questions, I would reach out to your local sales engineer or your local NHD software specialist, and they can provide you more information or maybe a more in-depth look at any of the features that we covered in this demo video. I appreciate you taking the time to watch this, and good luck in your manufacturing endeavors.